Hi, everybody. Thanks, Rue, and the organizers for giving me the opportunity to speak about what I think is really exciting application of BGC Argo data. I'm Nathan Briggs. I'm at the National Oceanography Center in the UK. Quickly, before I talk about my research, I want to just highlight what the UK is planning to contribute to BGC Argo. So far, we have funded the purchase of 30 initial full BGC 6-parameter floats. And our goal is to build on that as quickly as possible, build that up to a higher number and sustain it into the future. And so we're actively working to figure out how to fund that. But I think we're off to a promising start at least, and happy to contribute together with GO-BGC and other countries. Our first priority in securing these floats is to build out as quickly as we can the 1,000 float network that's been envisioned globally, profiling every 10 days. And then, if we can achieve that, we've gone for purchase of floats with high battery capacity, and so we'd be happy to discuss possibilities for how we can supplement a higher vertical resolution or temporal resolution without sacrificing the 1,000 float network in the future. But that'll be hopefully a collaborative decision. Okay, so now to my personal interest in BGC Argo data. My science focus, or primary focus, is carbon sequestration by sinking particles in the ocean. I'm interested in this because we believe that these particles supply the majority of organic carbon to the deep ocean, and this is important not only to feed deep ecosystems but also for long-term CO2 sequestration. And so this has been a challenging topic of study because it's quite hard to actually sample at the right scale these large, hard to find particles in the ocean, especially in the mesopelagic. Satellites don't really see these large particles like aggregates and fecal pellets that we think are transferring a lot of carbon to depth. And so really excited about the potential of BGC Argo to track these particles, find out what's happening to them, how much carbon they're sequestering. And really, for the first time, to do this at the scale that matters, at least for the CO2 question, which is global scale. So what sensors are we using for this? These are, Yui gave a good introduction yesterday, but just briefly to review, the two sensors that I'm going to be talking about are optical backscattering, which is depicted on the left, chlorophyll fluorescence on the right. Very similar in principle. You shine a light into the water, you look at how much light is coming back. If you are shining the same wavelength that you're looking at, then you're seeing primarily backscattering of light, and this backscattering can be any particle. So broadly speaking, it looks at concentration of all kinds of particles. But in the open ocean, a lot of these are primarily organic. So we can get an idea of organic carbon in particles. Then on the right, we have chlorophyll fluorescence. And instead of looking at scattered light, it looks at fluorescent light and using particular wavelengths that target chlorophyll. So we're really focusing on phytoplankton particles. So the subset of particles that are phytoplankton. And these sensors are easy to deploy on BGC Argo floats, but they're designed to just look at bulk particle concentration. I'm interested specifically in the large particles. So how do we isolate that? So briefly, here's a schematic of the sensor on the right. The sample volume it illuminates is about 1 milliliter, so it's a relatively small sample volume. And this actually comes in useful because if in that small sample volume, if you have a high number of small particles, you get a fairly stable signal with time as you move through the water, whereas large particles can cause jumps. So if we were going to look at this graphically, you see on the left your optical signal on the y-axis and time on the x-axis. And if we have the sensor on the right moving through the water or the water moving past the sensor, you can see that as long as you have your background of small particles, your signal is stable. But when a large particle is encountered, you have this temporary spike in the signal, and then you come back to approximately your previous baseline. Okay, so we can use that. We can take advantage of that the sort of random encounter of large particles in time or in the vertical, to separate out these spikes, which are large particles, from the background, which is small particles, as long as the particles are encountered one at a time. And now we have one sensor, one signal that now we can divide into two signals, and we can get two pieces of information about particles in the ocean, and even more potentially, because the height of this spike is correlated to the size of the particle. So what can we do now that we've divided our particle signal into two? Whether this is fluorescence, then we're dividing into sort of phytoplankton aggregates in the large size, and then individual phytoplankton on the small side. Or for backscattering, we're getting any sort of large particle that scatters light. It could be fecal pellets, it could be aggregates of phytoplankton, detrital matter. Here I'm showing an example of float data from the North Atlantic on the right. So here's what we've done. We've taken a lot of float profiles, time series, from 0 to 1,000 meters, and we divide the sample, the signal, into our spikes or large particles on the top. And so those are showing the aggregates with time and depth. And then on the bottom, we've got the background, which is our small particles. So this is really exciting what we can see from a BGC Argo float, just one sensor and lots of profiles. We have the mixed layer depth in black, and we can see on the top appearance of large particles, so phytoplankton aggregates, during a phytoplankton bloom. And then suddenly we see these particles sinking quite rapidly to 1,000 meters and presumably below. And what we were able to do in a paper last year was track these sinking particles, and we can see how many are lost with depth. And then what we're looking at is the appearance of small particles at depth, which we think are not sinking fast enough to get there by themselves. And so we infer that this appearance of small particles was actually fragmentation of the large into small. And so we could quantify the rate of appearance of the small particles and connect that to the loss of large particles and infer the role of this process, fragmentation, in controlling how much these sinking particles, how many of them reach a depth where they're going to be sequestered long term, and the carbon they carry is sequestered long term in the ocean. So this is really an unprecedented view into the interior of the ocean and what's happening to these quite hard to sample particles. So if you want more details on this particular study and the findings on fragmentation, that came out last year. But I want to move now to what I hope to do in the future. And I think we've just scratched the surface with this sort of small scale study. What I'm really excited about is with GO-BGC and the other contributions, we're going to, for the first time ever, have really true global scale coverage. And that's the coverage that is really important for a lot of the questions I care about. So with GO-BGC, we're going to use these same techniques to track sinking organic particles, and the fraction of them that reach the depth where they're sequestered long term, but at global year-round scale. So we're not going to be missing really anything. And then once you have global scale coverage year-round, this is really powerful, not only to get the right total number, but also we're going to see the variability, and we're going to be able to distinguish variability in space, in time, in season, year to year, and looking at the drivers of those variabilities is going to help us hone in on the mechanisms that drive carbon sequestration by particles. And then finally, the sort of ultimate goal is, once this global network, if we can sustain it, and I think we can, we're going to be able to detect not only the variability and the current state of sequestration of carbon by these sinking particles, but also we're going to be able to track global change as it happens, first interannual variability, then decadal, and then eventually, if we have long-term change, we'll be able to detect that over multiple decades. So I'm extremely excited about the applications of BGC Argo in general and GO-BGC specifically, which is really going to kick off this true global coverage that's the key to addressing a lot of the questions I'm interested in. And with that, I think I'm almost at the full 10 minutes. So thank you to the presenters and everyone for listening.
Thanks, Nathan. And it looks like we have a question here that I'll read from Lionel. So it seems that your spikes method needs a high temporal resolution. Can it still be applied to GO-BGC array that plans to use 10-day temporal sampling scheme?
Yeah,
If
so
so, is there a workaround?
yeah, that's a great question. So if you want to get the syncing speed, you probably want better than 10-day resolution. So if there's a subset of floats that sometimes sample at better than 10-day resolution, that'll be really valuable for getting the syncing speed. But just for looking at how many particles reach what depth, 10-day is plenty. And the more data that we have, the better. And in many ways, the true global coverage is going to be more important in the short term, I think, than getting that syncing speed. So yeah, it is helpful. It would be very helpful, but it's not necessary if we can assume a syncing speed from the few measurements that we have.
All right, thanks. We have another question, but I'll save that for the end. We can revisit it, and
Okay.
I think we should move to the next speaker. All right, so Marty, are you able to share?
I'm trying now. Do you see my screen?
Yeah, we see your WebEx window right now. So we
Great.
see the screen.
So
Yeah.
this means you're seeing my browser. Now you see my presentation, right?
Perfect. Yes. Thank you.
Okay, great. Thanks for having me today. I'm Martí Galí, a researcher at the Barcelona Supercomputing Center, and I'm going to talk about particulate organic carbon. And it's very nice that Nathan gave the previous talk, because what I'm presenting here builds pretty much on what Nathan has been doing. So basically, the aim of my work is bridging the gap between what biogeochemical Argo floats can see, and here you on the left you have a sketch, and what biogeochemical models on the right can represent. And for this, I'm using the Pisces version 2 model, which was recently, well, 4 years back, was updated with a much improved POC parameterization, which has variable POC reactivity, which is the key to be able to make these comparisons. But to compare these different observations and model outputs, we're facing several types of challenges. First of all, we need to estimate POC concentration from bioptical data. Second, we know there is an imperfect match between observed and modeled variables. And third, we can address this at different spatial and temporal scales. So first of all, regarding the estimation of POC and its correspondence with the model variables, here on the left, you see a plot from the paper by Nathan Briggs, and it's what he just explained, that we can separate, when we have high resolution profiles, and we can separate this baseline signal, which is somewhat proportional to small particles, approximately less than 100 microns, and the spike signal, which is proportional to the big, fast sinking particles. Then we need to apply empirical conversion factors, and in this study I used regionally varying factors from these different studies. Do you see my pointer, by the way? Okay. Anyway, and these factors also can vary through along the vertical dimension. And with all this, then we can do the matching between these two POC pools, small and big, from bioargo data, with the tracers in the Pisces model. And for this, here we match small POC to all phytoplankton, small and big, microzooplankton, small detritus. And we should include bacteria for a number of reasons, but for a number of reasons, we are not including them because they are somewhat implicitly included in POC in terms of stocks in Pisces. Then the spike signal, or big POC, is matched to the mesozooplankton and large sinking, fast sinking detritus in Pisces. Okay, then we have this global map, and each small black dot represents one grid cell where we have biogeochemical Argo profiles, and the yellow ones indicate a higher measurement density. And I'm doing the analysis for 4 different biomes in the global ocean: the North Atlantic subpolar gyre in blue, Mediterranean in orange, the subtropical gyres, except for the Indian Ocean, in yellow, and finally the subantarctic in green. And we are doing the comparison with 2 different approaches. So the first is comparing a global 3D simulation, climatological simulation, versus a gridded climatology of backscattering from BGC Argo floats that was then converted to POC. And the other approach, and the one that I would like to explain more in detail today, is the matching of annual time series from a single float against Pisces 1D simulations at selected locations. So to do this, for example, I'm showing here an example for the Labrador Sea. In 2015, we have this float which drifted in this area. The numbers here represent model grid cells. So we compared the mixed layer depth over the annual cycle from the float to all these grid cells in the model and picked the best match and used these physical fields to run the Pisces 1D offline. And now I'm showing how the comparison looks like for this particular case. So here on the left column, you have observations. On the top is small POC, bottom is big POC. In the middle panels, you have the corresponding small and big POC from Pisces. On the right, you have the ratio and some statistics in log 10 space. Then at the bottom, you have the vertical integrals of both small and big POC in model and observations for different layers: epipelagic, 0 to 200 meters here, mesopelagic, 200 to 1000 meters, and the total integral between 0 and 1000 meters. And I'm showing here that, well, the match in terms of vertical mixing is not perfect, and also we are assessing this vertical mixing in observations with different mixed layer depth criteria. But you see that the convection season is more or less well captured by the model dynamical fields from NEMO, is the physical model that we are coupling to Pisces. And then we see some interesting features. For example, in the model, we have a plume of slowly sinking POC, which we don't find in the observations, and hence this positive bias of the model here. We also see this deficit of small POC in the model in the lower mesopelagic in summer, whereas we see in observations that there is a faster transfer of small POC to depth. We also see this trend to general overestimation of big POC by the model, but I recall there is a lot of uncertainty in the conversion factors, particularly for big POC. And, well, we see the model is, in terms of vertical integrals, is doing a great job for the epipelagic, a decent job for the mesopelagic, and, well, when we add them together, it's also quite good. And there's some compensation between different types of biases. Now, what I showed for this particular float is something we did for another 50 annual time series for different regions, is what I show in these scatter plots. And, well, there's lots of information here, but the summary is that, well, you have, in the scatter plot, you have Pisces on the y-axis and BGC Argo standing stocks on the x-axis. So this black line is the perfect agreement. And in general, you can see that the model is doing better in the epipelagic than in the mesopelagic. It's doing better for small POC than for big POC. But what I found striking is this high correlation between modeled and observed big POC, despite the huge uncertainties. And this indicates there is something some fundamental processes that are well captured by the model, and it's very encouraging. And we also saw that there is some regional, there is some geographic coherence in the mismatch patterns, which tells us about different processes that need to be better represented in PSCAs. And this brings me to the conclusions. So basically, we observed that PSCAs version 2 can reproduce with good skill the main features of POC dynamics observed by BGC Argo. However, we notice comparison is affected by several layers of uncertainty, from empirical POC estimation through the matching of variables, matching in space and time, uncertainties in model physics, and so on. But if we are able to overcome somehow these uncertainties, we can infer how to improve the model in terms of the parameter values and even the model equations, ultimately. So what we are currently doing is this. We are trying to optimize POC cycling parameters in PSCAs using BGC Argo observations. And for this, we use the genetic algorithm, which we embedded in a workflow manager to be able to run thousands of simulations automatically and in parallel. And we didn't forget about the 3D context. So we are trying to put these improved model parameterizations back to the 3D model to better estimate POC budgets in the North Atlantic in the 3 dimensions. And that's all. Thank you for listening.
All right, thank you. Do we have a question while we're transitioning to the next speaker?
Yeah, would you invoke disaggregation to get the big into the small? In that fit?
Yes. Do you refer to this slide, perhaps? No, where we see this simultaneous increase in big and small POC. Yes, I think it's fragmentation of large aggregates, and the problem is that the way the model represents these processes is not ideal, but that's what we are trying to pin down.
Excellent, thank you. We are ready to move on to Mariana's talk. So welcome, I'll let you take it from here.
Thank you. I just want to say, Nathan, your methodology is famous because I have been using it as well. Very good. Good morning, everyone. Today, the title of my talk is Constraint on Net Primary Productivity of the Global Ocean by Argo Oxygen Measurements. This paper is coming out, I think, in the next few days. It's provisionally accepted in Nature Geosciences, and it's in collaboration with Ken. We are both at Embari. So we all know the importance of primary productivity. It's the driver of the biological carbon pump. And primary productivity can be estimated from DO oxygen cycles as gross oxygen production. And then we can convert into units of carbon to net primary production. This has been done using gliders data and high sampling frequency floats. For example, Baroni and collaborators in 2019 have a very nice paper and outline a very good methodology for estimating this gross oxygen production. But it's not the reality for the global ocean. We don't have a lot of high sampling frequency floats. So our idea for this work was to use Baroni's methodology for these high sampling frequency floats and apply for the global data. This was inspired by Gilly's work. She measured global diurnal temperature variability using the Argo floats. And she used anomalies in temperature at noon as a reference point. And she traced this very nice diurnal variability in temperature at the different latitudes. So our idea was to apply more or less something similar to this. Okay. So why does it matter? Why the importance of estimating net primary production using biogeochemical floats? So our satellite-based products that estimate NPP and our biogeochemical models, they need observations to work very well. And right now, the observations that we had that don't include these float estimations are from light and dark bottle incubations or radio-labeled carbon incubations or using triple oxygen fractionation. And then mapping the left is how much, where our data is. So as you can see, we have a lot of gaps. And this makes our models and our satellites sometimes not match with our observations, just as we can see for net community production in the right. So what did we do? Well, we used the entire fleet of biogeochemical floats, but we removed a certain portion of floats. We removed floats that were in shallow regions, so in regions that were sampling under 2,000 meters. And we also removed floats that sampled at a fixed hour, because any offsets in the oxygen sensors would carry this offset signal into that fixed time point. So for example, in the Northern Hemisphere, we had about 25,000 profiles from all the floats. But when we removed these floats that sampled at fixed depths, we ended up with about 9,000, about a third of the amount of floats, amount of profiles that we could use if they were not sampling at fixed times. Then we fit our data into a method developed by Baron from 2019, and it's a least squares function. So we calculated our oxygen anomalies from the oxygen concentrations that we found minus the oxygen saturation. And by fitting our data to his function, we could see this nice daily cycle over here. So this is for the Northern Hemisphere, just to illustrate. So first we integrated this gross oxygen production above the euphotic zone and at latitudinal bands, so we could remove the biases and take a look at similar latitudes first, and then we sum this gross oxygen production to estimate globally gross oxygen production. Also, we validated this methodology using data from HOTS and BETS, because we have a lot of gross oxygen production and that primary production over there using the very well-known techniques. We wanted to compare our estimates to their techniques. Then we converted from gross oxygen production a day to net primary production a year by multiplying by a conversion factor. So here again, that global image of gross oxygen production estimates, not using float data on the top, and by using all the floats that we used in this work, this is the coverage that we get, which is very improved. So for our results, gross oxygen production in the upper ocean at HOTS, for example, at HOTS, I always say HOTS. At HOT, our float estimated 1.5 millimolars of oxygen per day versus 1.3 from the other study. And once we integrate to the euphotic zone, we have 103 versus 103 to 111 from other methodologies in the same region. When we go to BETS, we have a little bit of a higher estimate of 148 versus 70 from a previous work. And we can see the very nice daily cycle in the top graphs over here. And since we have a lot of data in those sites, we could also estimate an annual cycle. So as we can see in HOT, we have kind of a steady state gross oxygen production throughout the year. And when we move to BETS, we have a decrease throughout the year, which is already very knownly observed. And by comparing with net primary production, which is a little bit is lower than gross oxygen production, but we see a similar seasonal cycle. And this method can also be propagated to the depth. So when we pick up this gross oxygen production estimated from all of these latitudinal bands and we sum it, and we add a little bit of the gross oxygen production that we would observe in the global ocean, we add a gross oxygen production of 11.9 picomolars of oxygen per year. And a study developed by Yibing Wang that is going to also present tomorrow is going to give I think the R tutorial. He estimated using machine learning techniques that the GOP would be between 9.5 to 12.6, which our result is more or less in the middle of what he estimated. When we estimate the net primary production, or the GOP converted into carbon units, we have a 53 petagrams of carbon per year, which is very similar to what models are measuring right now. The most recent models measure 52, and ours is 53, which means we are going in a good direction. And when we take a look at latitudinally, the floats agree in general with the models, but we see a discrepancy in the equatorial zone. But we have a nice same tendency over here with the latitudes. So in summary, gross oxygen production and net primary production can be estimated using a global array of floats. So treating all the floats as a global array, we have numbers: gross oxygen production, 11.9 petamoles of oxygen per year, and net primary production, 53, more or less 53 petagrams of carbon per year. Our numbers agree with models, so I think we are on the right tracks, and models are on the right tracks. And we hope that this float data can be used to optimize satellite and model outputs. And now that we increase the number of floats that are going to be deployed in the global ocean, we can fine-tune these numbers over here. And but this global array allows us to understand a multitude of biogeochemical processes, and dealing with many floats at the same time is very interesting. And I am very interested in the POC production and export that you saw from the previous talk. So just as an example from the South Pacific Ocean, I am analyzing annual cycle of POC production and export using Nathan's methodology. And for example, what I could see just as a sneak peek is that there is seasonality in the transfer efficiency of POC from the upper ocean out of the aquatic zone. There is an average of 67% of all the POC that is produced is going to be exported and protected from the atmosphere, but it varies a lot. And with that, thank you so much.
Thank you. So we have a question. If the function that you fit to O2 takes into account the day length.
Yes. It takes into consideration the local time and the light intensity. Mm-hmm.
All right, and if we have probably time for one quick other question, otherwise we'll move on. All right, so let's continue on, and Fei Chai can take over from here.
Thank you.
Yeah,
Thank
there
you
we go.
for the organizers. Thank you for the organizers invite me to give this talk. And then for the last 6 years, I have been splitting my time between the Second Institute of Oceanography in China, and then also so I'd like to acknowledge my co-authors at those two institutions. So I'm going to tell you two topics. One is China's ongoing activities and plans for the BGC Argo. And then I'm going to tell you two short stories using the BGC Argo we deployed in the Northwest Pacific. So since 2018, September, the Second Institute of Oceanography deployed a total 13 BGC Argos in the Northwest Pacific. And those roughly the location of those 13 floats deployed. and in combined with Japan JMA and then AOML for the Equatorial Pacific region. So there's a 9 still in the water. We recovered a total of 4 BGC Argo floats by fishing boats. And then so I will tell you a little bit how we did that. And so there's another 5 floats with all 6 sensors will be deployed in the Pacific region if we get those float purchased and soon. And I think so. In September 2018, as soon as we deployed these 2 floats in this region, there were 2 strong typhoons hitting Japan. And then those are Category 5 typhoons. It caused a big damage on land. And then in particular, Typhoon Trami, when I saw the trajectory and it's going to overpass one of the floats, and we altered the sampling frequency from 5 days to daily. So here's a trajectory. Here is our floats. And then, so from a 5-day and then to 1 day. So this the right dots here are the surface of chlorophyll. So the black dots are the MODIS, and you can see because the cloud coverage, and you don't see of the changes. And then unless you're lucky, you got the one spot here. But we got a continuous surface of chlorophyll increase. And then not only that, we can look at a upper 200 meters of how this chlorophyll profile changes. You can see the mixed layer deepened during the passage of the typhoon. And then that bring the increase of upper 50 meters of chlorophyll, but a decrease at the subsurface chlorophyll maximum, roughly about 100 meters. If you integrate of the chlorophyll, say from surface to 150 meters, and then the total chlorophyll stays flat. So if you look at the top 50 meters, there's increase, there's a decrease below 50 meters. So there is no new biomass generated and then with this particular typhoon events. The reason is the neutron climb in this region is deeper than 100 meters. So the wind mixing generated by typhoon cannot bring the nitrate up to the euphotic zone to support new biomass. So the growth, therefore, is really a purely physical mixing of the vertical profiles. So because the same float, and then we forgot back to the 5 days of sampling. We just left it on and throughout the winter. And then by June 2019, there was a fishing boat near our float. We stopped the sampling. It took the fishing boat about 8 hours to recover. And then there's no biofouling. We sent back to NKE, changed the battery, and this particular float back in the water to continue. So throughout the winter, we saw very interesting phenomena. That is the winter storms and passing through this region at a frequency about 8 to 10 days. And then during each storm, the mixed layer deepens to 200 meters. Between the storm, the mixed layer shows to about 30 meters. Every time the mixed layer shows, and there is an increase in chlorophyll in POC. And then until the next storms are passing through, and then they bring the particles and then also the POC to the depths. And you can see this and down to about 400 meters. So there is a mixed layer carbon pump that is you can see during this shoaling of the mixed layer, and then the chlorophyll increase, the POC increase in the mixed layer, and then below the mixed layer, from mixed layer to 400 meters, there is a delayed increase, roughly about 2 to 3 days. So you can calculate this export, and due to this, if we sampled this 3 months, January to March, and we called a total 7 those storms events. So if you calculate the season, those total export, it's 8.9 grams carbon per square meter, and just in this region. If you sample at the 5 days frequency, and then you reduce down to about 1.2, that's almost 1 order of magnitude a decrease. If you sample at the 10 days of frequency, you missed those winter storms generated POC export completely. I think this is an illustration. To summarize this, with the GO-BGC, and then we have a global coverage and at the 10 days of sampling frequency, but we need to pay attention to the sampling frequency to capture those biological, biochemical processes. We use the one particular floats to illustrate the value of the daily profiles, how this capture the typhoon, the winter storms, and then it's really this one particular float. We also look at another float for the South China Sea. It went through the similar process. The nutrient line so deep, the typhoon passage didn't bring enough nutrients to generate a new biomass. I think this a winter storms and then a generated bloom is relatively new. The most of the physical biochemical models really need to consider those extreme the weather events and how that impact on the biochemical processes. I think several of us on this call, we worked together for a year, is really to bring all the observations together from the satellite, the ship-based, and the other autonomous platforms and the sail drones, wave gliders at the surface, that not only to give us the global coverage, but also the finer spatial coverage, such as the mesoscale and sub-mesoscale features. And then, so that will inform the physical chemical models and to resolve those phenomena. And then, that go back to guide a different observation network designs, I think. So I will stop here. Thank you.
Thank you. So we have time for a question.
I had a quick question while we're doing this. This is George. That was a fascinating talk, Professor Chai. I was curious, the fishing boat took 8 hours out of their day to recover the float. Was there any compensation for that? Or how did you convince the fishermen to spend a day hunting for a BGC float?
Of course, there are some incentives, and then so we work with the fishing companies, and then tell them the value of this, and then we definitely cover their fuel, and then some compensations, but it is really minimum compared to the price we pay. The shortest that we got recovered is about 5 hours, and then so you have to know their location, and then you start profiling the day before, and so that particular float, we learned the lessons. Actually, we paint with orange instead of white, and for the redeployment. So we covered the 4 total. So we have pretty good luck so far.
All right, and any next question up on here is any plans to extend the typhoon analysis to the global array?
Yes, we have done that for the South China Sea, and then we look at the other locations. Again, this is the regional dependent, and then I cannot draw a conclusion on the global scale. we work one float at a time. And it's really the temporal sampling frequency for the typhoon before and after. So.
All right, thanks. Next up, Emily Osborne.
Great. I hope you can see my screen and hear me okay. Awesome. Hi, my name is Emily Osborne. Thanks so much for the invitation. I'm looking forward to sharing with the group some of the work that NOAA is supporting with respect to BGC Argo. I'm a researcher working at one of NOAA's laboratories, the Atlantic Oceanographic and Meteorological Laboratory based in Miami, Florida. You'll also be hearing from Andrea Fossbender today, who is also a NOAA researcher at our Pacific Marine Environmental Laboratory, as well as two NOAA Cooperative Institute investigators, Rue, who we've heard from today, who's affiliated with WHOI, and Sarah, who we heard from yesterday, who's with Scripps. So just given the demographics that Ken was sharing yesterday about all the registrants for this workshop, I just wanted to kind of give a little bit of orientation to NOAA as an agency. So we're a U.S. federal agency. Our mission is to understand and predict changes in climate, weather, oceans, and coasts, and share that knowledge and information with others to conserve and manage coastal and marine ecosystems and resources. So what we've heard over the last couple of days with respect to BGC Argo, we all know that this new tool fits really squarely into meeting this NOAA mission. So over the last couple of years, NOAA has initiated several BGC Argo research projects at our NOAA laboratories, AOML and PMEL, as well as has initiated some projects at NOAA Cooperative Institutes with our academic partners. So AOML is focusing on conducting research in the Atlantic Basin as well as the Gulf of Mexico, and PMEL is carrying out research in the Pacific Basin. And the science that we're doing with respect to BGC Argo is linked really intrinsically with the more operational work that our agency carries out, including producing weather forecasts, ecosystem assessments, looking at fisheries. We heard from Kara Wilson yesterday, who works with NOAA Fisheries. So we're really actively trying to build those connections with this research branch, focusing on BGC Argo and making that connection to some of the more operational needs of our agency. So to take a dive at a very high level, because we just don't have very much time, into a handful of projects that NOAA has begun supporting. At AOML, I'd be remiss if I didn't at least mention that we have the Data Assembly Center, or US DAC, as Tanya was talking about yesterday. So we have a growing staff and expertise that's building out our US DAC in order to be able to decode our BGC Argo data from a number of different types of floats and really process all of those different sensor parameters, conduct real-time quality control, and serve that up to the public. At AOML, we're also standing up a small research group, and we are deploying a pilot array of floats in the Gulf of Mexico later this year in September and October. We have 4 Apex floats, which, as you can see here, we are planning to deploy in this configuration. The Gulf of Mexico is an incredibly underobserved region of the global ocean. And so we're really excited to look at this unrivaled data set and analyze things like ocean acidification, air-sea CO2 exchange, how the biological carbon pump is functioning in this region. Also thinking about some of the work that Fei Chai has done, looking at episodic storm events and effects on biogeochemistry. And also another thing that is really important too, particularly the US Gulf Coast, are the initiation of harmful algal blooms, and if we can learn anything from our BGC Argo floats about conditions that might initiate those blooms, we're looking to kind of research all of those things. I'm going to pass it off to Andrea, who's going to talk a little bit about the work happening at PMEL.
Great, thanks, Emily. Hi, everybody, I'm Andrea. I'm here to talk a little bit about the California Current Pilot Array. This array was initiated by a proposal to GOMO in 2018, led by Greg Johnson and the team of researchers shown there. And the proposal was to deploy 5 BGC Apex floats in the California Current Large Marine Ecosystem. And the data from these floats, I should mention, these floats were built in Steve Reiser's UW Float Lab, as well as Ken Johnson's MBARI Chemical Sensor Lab. And the data from these floats are being transmitted and processed through the UW and MBARI data streams to AOML. The first float, which is highlighted in orange and some of the data are shown on the left, was deployed in August of 2020. And the 5th float will be deployed next month on the West Coast Ocean Acidification Cruise that's currently being led by Dick Feely and Brendan Carter. And just to give some background for the team, I joined PMEL to lead the BGC Argo effort just last September, and Jonathan Sharp, who's a postdoc in the group, joined shortly thereafter. And he's leading a couple of projects focused on biogeochemistry in general in the California current system, and a few particular things targeting use of the floats to see what we can learn from these new data sets. Hartmut Frenzel joined earlier this year, and he's leading the BGC Argo data streams, data management, and delayed mode QC at PMEL. And just to give you a little bit of background on our science goals, the California current system is a very productive eastern boundary current that's important for lots of fisheries. And so there's a lot of interest here from NOAA. And one of our goals is to study both the timescales and the spatial patterns of biogeochemical variability throughout this domain. In addition to the observations, this project also includes a modeling component led by John Dunn at GFDL. And he's had a couple of postdocs who've been working on analyzing how well the GFDL's Earth system models do in representing the biogeochemistry in this region, and also how the models can be used to fill in observing gaps from the floats, which we sample at the 10-day frequency. For next steps, we'll be deploying 2 additional Seabird BGC floats in the next year or so, depending on when they're available. And our goal is to continue building out the array and also to engage with scientists in other disciplines such as fisheries or data assimilative modeling to have people use these data for new analyses. And so with that, I'll pass on to Rue.
All right, so at HUI, we also are starting to expand NOAA's Argo presence into BGC. And so HUI has been a long partner in the Core Argo program. And we just deployed our first BGC floats this May, and those were in coordination and cooperation with NASA as part of the Exports Biological Carbon Pump study. Those 2 are shown on the map here. The orange one here was deployed into anticyclonic eddy, and it has actually continued. This map's a little out of date, but it's still spinning around that eddy, while the second float has headed to the south. And we're looking forward to deploying several more into the Atlantic, targeting the Bermuda Atlantic time series as we start to build out a NOAA-funded Atlantic pilot array. And in addition to the float deployments, we're also working in the lab to better characterize the platform and some of the sensors, and we'll be conducting some tests to better characterize the dynamic response of some of the BGC sensors. And below is just an example of some of the early profiles we're collecting from our first deployment. All right, on to Sarah.
Great, thanks. So Steve Reiser got to talk a little bit about some of the work that Scripps has been leading with regards to both GO-BGC and the NOAA BGC Argo. What we've been working on is primarily the development of our new BGC solo model, which is photographed over here on the right. And it's just based on the Solo 2 design, which is a core Argo float, and we're adding all 6 of the BGC sensors. And we are almost done with our first prototype, and the plan is to deploy the first really 6 floats coming out of Scripps are all going to go to the equatorial Pacific. And so we've been focusing our efforts there. Hopefully in November, we'll deploy the first 4 and then another 2 at the beginning of 2022. And this effort has been in collaboration with Todd Martz and Lynn Talley and with Matt Masloff. You heard a little bit from Matt Masloff yesterday about some of the modeling efforts, the reanalysis efforts going on in the Southern Ocean. And he's also been working on data assimilation with the BGC component in the equatorial Pacific. And then I should mention, in addition to that, we've been thinking a lot about protocols, about really the technology and protocols for checking out the sensors to improve float performance. And with that, I think I'm handing it back over to Emily.
Yes, thanks, Sarah. So a couple take-home messages that we wanted to leave you guys with is that NOAA's growing its presence and capacity to support BGC Argo. We're building out staff and expertise at our labs, and certainly leaning on the expertise that currently exists at our cooperative institutes to carry out research. As Lynn was talking about yesterday, there are certainly opportunities to leverage existing NOAA cruises, such as cruises like GO-Ship or the ocean acidification cruises like the one that's out now that Andrea has a float going out on of her float deployment that currently have plans for collection of excellent calibration data sets that are important for your deployment opportunities. We're going to hear tomorrow from Emily Smith, who's our program manager for BGC Argo at NOAA. We're really optimistic that funding will be favorable for NOAA and also BGC. The president's budget had some really great language about this that came out. And given that and growth, we hope to see that this lab and CI expertise continues to grow. And then also we might have some external competitive opportunities for the broader US community to compete for funds. And last but not least, we are really open to building connections and partnerships and collaborations across research communities to use the BGC Argo data streams. We really want to see these data streams being used to their maximum potential. So if you're excited about where some of the pilot arrays are or some of the work that NOAA is carrying out, please don't hesitate to contact us. We would love to hear from you. I'm just going to leave the contact info here, and hopefully slides are available to all the participants later. So thank you so much.
Excellent. So we have one quick question here, and I'll open up this also to probably to Ken and Steve to comment on this, since they've deployed more BGC floats than most of us. Is what are the most common failure modes in BGC sensors?
Good question, and there's no simple answer to that. So first of all, we do track the statistics for all our sensors, and fluorometers rarely fail. Oxygen sensors, when they fail, it seems that they just stop sending. They still communicate, but the data is like all zeros. Not sure what that internally means. Not a very high percentage of the oxygen sensors do that. Nitrate sensors, essentially, when they fail, could be fouling. It's failure of light throughput in the system. So you see them slowly, lose light coming back to the sensor, and eventually, then if there's not enough light, then you can't get the error in the nitrate concentration just goes up and up, and we have automated criteria that will just reject it. But basically, loss of light throughput in the sensor. And for the pH sensor, it is most common failure mode is the seal on the ISFET chip. So little tiny silicon device, little tiny O-rings, and the machining tolerance is required to compress the O-rings adequately for 2000 decibars is right at the limits of what people can machine accurately. And so we're have new designs in the water now that does away with O-rings, but it's failure basically of the O-ring seals on the ISFET chip, leading to leakage and killing the sensor. The good news is that failure of any one of these sensors doesn't take the float out. So you lose an the worst thing is to lose the oxygen sensor, because we do use that for essentially to help quality control the other sensors. But you lose a nitrate sensor and you've still got pH and oxygen and biooptics. So you have some fractional decrease in the float capability, but it's not the end of the float.
Thanks, Ken. All right, let's move on to Christina Schallenberg.
Good morning, I should say. Thanks for the opportunity to let me speak at this event. Also, a shout out to my co-authors here, Sophie Bestley, Bojana Wojtaszewicz, and Robert Strapek, all from Utah, and Cesaro here in Hobart, Tasmania. And I should also mention that what I'm showing here was actually very much inspired by an analysis that Josh Plant shared at a previous workshop. So yeah, shout out to him too. Thanks for giving me the idea here. And what I'm going to talk about is the Southern Ocean in particular, and mostly working on, or actually entirely working with French floats. I think it's all NKE. And I'm interested in the Southern Ocean in particular because I care a lot about fluorescence. And we do know that globally speaking, the fluorescence sensor has an offset, I guess, to what the actual chlorophyll concentrations would be, that is around factor 2. And that's what you can see here. That's the Rosler paper that most of you will be familiar with. But we do also know that regionally, there's actually huge differences. I can't see my mouse, there it is. Huge differences. And the biggest difference appears to be in the Southern Ocean. And it's not only that here the slope factor between fluorescence and chlorophyll seems to be the highest, but it is also very variable, which is partly captured in the error bar, but it's actually quite a bit worse than that. So that's something I'm interested in to figure out what is up with that. And oops, why do I not? How do I move forward? Oh, there we go. And I'll skip straight to my hypothesis, which is that ion limitation is a determining factor for the fluorescence to chlorophyll slope or ratio in the Southern Ocean. And I'm saying a determining factor because I will not claim ever that it's the only one. There's certainly species composition, a lot of other things that will play a role. But it does seem to have something to do with it. And that's partly intuition, thinking about, you know, what happens in the cell under ion limitation, if you think about the physiology. But also Robert Strapag actually has some lab data, and this is an example here that shows that here we have the growth PFD, so what light they were grown under. These are really lab bugs, but it's Phytoplankton antarctica, a Southern Ocean species. And we can see that when they're grown under high light, high iron, sorry, they fluoresce quite a bit less per chlorophyll than under low light. Low iron, apologies, it's 3 a.m. So that, you know, between, yeah, just some intuition and this kind of data, I was like, oh, it's maybe worth having a look. And I'm doing this entirely with float data, so no satellites or HPLC here. So there's about 27 NKE floats that had radiometers, because I do need radiometers for this analysis. And with these radiometers, you can actually estimate chlorophyll. I wasn't at the meeting yesterday, maybe Josh has talked about it at some point, but basically you can use the extinction coefficient of light to estimate chlorophyll. And in blue waters, case 2 waters, that works reasonably well to actually get a good estimate of chlorophyll, which of course will be integrated over a certain depth layer. So I'm using floats with radiometers to get my chlorophyll. And with that, and having then an NPQ corrected fluorescence sensor on the float as well, I can get my fluorescence per chlorophyll ratio for a certain depth layer. Now, how do I get the ion limitation? That's a tricky bit. And again, I'm getting this from the floats, believe it or not. So I use the fluorescence and the PAR data, so the light data from the radiometers, to estimate ion limitation by analyzing the relationship between non-photochemical quenching and PAR. And this part I will explain a bit more. So here's just an example of what a fluorescence profile from one of those floats looks like. The blue dots are the fluorescence data as they come, and this is high resolution data, which is really nice to work with. Then the red line here, which becomes the green line here, is just a running median through these data, just to smooth them out a bit. And this is daytime data, and you can clearly see that there's a reduction in fluorescence as you go towards the surface. And then here are 2 NPQ corrections that I tested. One is using the backscatter signal and a constant fluorescence to backscatter ratio to get this line. And then the purple line, the straight line, that's just a Zingenal correction, which I actually prefer. And so then here you have my corrected fluorescence trace. And the difference between the two is NPQ. And you can use these 2 terms, the corrected fluorescence FM and the uncorrected fluorescence FM prime, to plug them into this equation, which is a Stern-Volmer equation for NPQ. And then you can plot that NPQ over that depth range against your incident light that was measured by the radiometer. And you end up with something like this. That's the blue dots here. So that's like on from the moving averages here, moving medians. And you get these dots. And you can fit a line to that follows this equation here, an exponential function, where you have 2 parameters that you need to fit. So you have your NPQ max here, and you have your alpha NPQ, this initial slope. And I'll tell you right away, this doesn't always work. So there's a lot of profiles where you have to reject this. So I'm using a pretty high R squared as my cutoff to be sure I really get data that I can believe. But you can do this sort of thing, and it turns out that non-photochemical quenching actually has something to do with iron limitation. So this is some previous work I did here from the Southern Ocean time series. Let's focus on the left for now. We have fluorescence per chlorophyll. This is from underway data. The fluorescence was measured just by a fluorometer, not at all corrected. And the chlorophyll is from an AC9, so it's as good as it gets, I guess, for underway data to get a good idea what chlorophyll really might be. And then I also have the light that was measured above the water. And I was lucky to be crossing the subantarctic front back and forth. And north of the front in the warm water, there was iron. And in the south of the front, where it was colder, there was no iron, or very little iron. So you can assume iron limitation here, not so much iron limitation there. And you can see two things. One, again, fluorescence per chlorophyll is quite a bit higher under low light for the iron-limited bugs, but also they're engaged in a lot more NPQ. I mean, I'm not the first one to really show this. This was actually buried in other studies, like Nina Schubach, for example, has seen this before, and she's a co-author there. But then Tommy Ryan Keogh and Sandy Tumala went further and did this sort of analysis, like the plot I just showed you, the fit you can do with the NPQ, and they showed that this initial slope seems to be related to iron limitation. So iron limitation leads to a high initial slope for NPQ and low iron limitation to a lower slope. They didn't find so much of a relationship for NPQ max, but it's still potentially a very handy thing to explore further. So that's what I used, and that's how I get the data that you will see in the next figures here. So first of all, let's look at fluorescence per chlorophyll, where the chlorophyll, again, is from the KD, from the radiometer. And most of these floats are in this area of the ocean anyhow, so this is probably 80% of the data I have. But it's just interesting and instructive to look at Kerguelen Island here, because we know that downstream of this plateau, so over here, there's usually less iron limitation, certainly during the spring and summer, because of input from the plateau, iron input. But upstream, there's high iron limitation year-round, and we can see right away that over here we have a higher fluorescence per chlorophyll ratio than downstream. So in principle, this seems to work, but of course we won't stop there. So my friend Sophie Bestley, who's a statistician, has done some fancy GAM, what is it again? Sorry, general additive mixed model, to not just look, of course, at our initial hypothesis, the alpha and iron status indicator thing here, but to also see what other things actually may have an influence on the fluorescence per chlorophyll ratio. And so what you see here is 6 factors that she tested for, so they're always on the bottom x-axis mentioned. And then the stars here tell you whether they're actually significant for this mixed model. And you can see 5 of them actually are, well, highly or very highly and highly significant. So mixed layer depth is not. But the highest one really seems to be this alpha, this iron status indicator in all these things. So this is satisfying intellectually because, yes, iron does seem to matter. I'm very happy with that. But of course, there's 2 things I want to do with this, and that's figure out what's going on, because that interests me, basic science. But the other thing is, so how can we use that to actually do better calibrations for our Southern Ocean fluorescence sensors? And in particular, I would like to be able to use that in some fashion, even on those floats, which is by far the majority of the floats that do not have radiometers. If you have a radiometer, great, you can do your KD chlorophyll. But if you don't have that, what do you do with your fluorescence sensor? And so a few things that are coming up, and this will be a publication hopefully in the next few months as well, submitted in the next few months. So Bojan, actually, she has done this by now. I made the slides like a week ago. She has now done a matchup with satellite data, and it actually looks beautiful. So that's good news for this KD chlorophyll. It seems to work. Then, as I said, find a way to make this information useful for floats that don't have radiometers. And for example, this NPQ max might be a better bet there to use than the alpha NPQ, because you can estimate that with reasonable confidence if you don't have PAR data, versus the alpha is super sensitive to a good PAR estimate, which you won't really get if you don't have a radiometer. Finally, it turns out that the variability of the slope factor, so of this fluorescence per chlorophyll factor on a given float, is not very high. So from a QC operator's perspective, this could become in handy. So this is what this figure shows, and that's the last thing I'm showing. It's just the 27, or I think it's 25 only, floats, and you can see the slope factor for each of them in this plot. And you see there's not that much variability per float, probably partly because they tend to use move more along latitudes than cross latitudes, so they stay probably in a reasonably constant iron limitation status. So this might be useful, so we could maybe just find a factor for a float early on and then just use it until we do DMQC properly or something. And that's it from me. Thank you.
All right, thank you. We have two questions that are really related questions here, so I'll try to combine them. And I think it's pointing at what the mechanism is, for example, in the photosynthetic apparatus, that how iron limitation would lead to changes in NPQ.
Okay, so one thing that happens is you just have less photosynthetic transport chains that you can make if you don't have much iron. So what phytoplankton, especially in the Southern Ocean, tend to do is they make bigger antennae, and that would just lead to more loss of energy to fluorescence in those bigger antennae. And they may even, this has only been shown as far as I know still for cyanobacteria, so it would be nice to show that for more species, that they might even decouple total, like chlorophyll completely from anything else, that just sits there to be ready whenever they get iron to recouple it. And then also will fluoresce. So those are two sources of fluorescence that would be very unique to iron limitation. And for the NPQ, though, for the NPQ side of things, the theory is that, again, because of these limited photosynthetic transport chains, basically that is very similar to being extremely sensitive to light. So they just basically get sunburned faster, and therefore it would make a lot of sense for them to also invest in a strategy that would protect them. So yeah, iron limitation in a way is like getting light stressed at lower light, and therefore you have to do something to prevent damage.
All right, great. Apologies, I'm going to keep us moving since we're running short on time. So let's move to the last speaker for this session. Miguel, take it away.
Okay, I'm Miguel Santos from Portuguese Institute for the Sea and the Atmosphere, a member of.
Miguel, could you try to speak up a little bit? We're getting it's a little hard to hear you. Thanks.
Okay. I'm Miguel Pérez Santos. I'm from the Portuguese Institute for the Sea and the Atmosphere, and also a member of the Center of Marine Science of the University of Algarve. And I'm presenting the importance of using BGC Argo floats to study the Mediterranean outflow. We are in the eastern boundary current, the Canary currents. It's like the eastern boundary currents of California and Benguela. But our system has a difference, that is, there is a discontinuity of the system and the outflow of Mediterranean water into the system, and this make a tank of more saline water spreading onto Atlantic Ocean, North Atlantic Ocean. And this could have very important implications for the thermal circulation if there are differences in the characteristic of this water, like the increasing of salinity. As you can see, this Mediterranean outflow spreads along the eastern boundary current, eastern part of the North Atlantic. And as you can see, this is a float that was deployed in 2016 and get into Mediterranean outflow, and it flows for about 40 years, almost 5 years now, along the west coast of Portugal and Spain, and now in France. Because this Mediterranean water is more or less flowing more or less into 1,000 meters, so it's where the parking depths of the cargo floats are. this Mediterranean outflow has two characteristics, two biogeochemical characteristics. That is a low nutrient contents and also a low oxygen content. Another important features that are associated with this outflow is the Mediterranean eddies, that called MEDIs, and that spread also onto all the North Atlantic, and their origin is mostly on this southwestern coast of Portugal, and most of them flow to south and collide with these seamounts. Last year, in collaboration with Argo France, we deployed two floats in the Gulf of Cadiz, and one go inside the Mediterranean, but the other one start to flow to the north, but probably get trapped in a MEDI, and now is flowing to the south. And if we look to the dissolved oxygen profile, you see that in the core of that Mediterranean outflow, there is also a low oxygen content. This is another example of another profile also, as you can see. And the main message I want to leave is that because this Mediterranean outflow is an important saltite source for the North Atlantic, it is important to understand, to study their variability. Also, the BGC characteristics of the Mediterranean water could be studied with the BGC Argo floats, so it's important. Argo floats are an important tool to follow MEDIs and to understand their characteristics and variability, mainly the importance of what will be the impact of their collisions with the seamounts and on the habitats of the seamounts. The Gulf of Cadiz circulation dynamics pose interesting challenges for its monitoring with Argo floats, because it's a very dynamic system, and because the parking depths of the core Argo floats are on the core of the Mediterranean outflow. We are now investigating the best configuration of the floats to stay stay more into the Gulf of Cadiz, to stay more time in the Gulf of Cadiz. And we have very few observation of the Gulf of Cadiz, and the Argo floats could be an important tool for extend this observation, and also the sparsity of MEDIS observations prevent an assessment of their importance for biogeochemistry of the North Atlantic Ocean. To finalize, I want to tell you that we intend to deploy next year when BGC complete float with the 6 sensors in the Gulf, and also another one with only with oxygen sensor, and also 4 core Argo floats in the Gulf, and trying to observe best this system. Thank you very much for listening.
Excellent, thank you. And thank you to all the speakers for a really great series of talks. Let's we have just a couple minutes for questions right now. feel free to ask a question for Miguel or for any of the other speakers if there's some further questions that came up.
I don't see any questions in the chat or Q&A.
I have a question, and I can't type fast enough to use the chat, George. And,
Go ahead.
And are we so do you think that there is a nitrate signal as well in the Mediterranean outflow that you would see? So you're going to put a 6 sensor float in. Will that be a nitrate minimum?
Yes, I think so. Yeah, that is for by some cruises that we have there. We have indication that is lower of nutrients, so lower of nitrates. Yes, so we're going to put a nitrate sensor. Yeah.
All right, and I'll highlight, I guess everyone can see the other question that came up in the chat about whether the fluorescent changes were driven by quantum yield or the chlorophyll-specific absorption. And sounds like Christina would think about it more, but it sounds like like that would be the case, that it was driven by quantum yield changes. I'll summarize another comment that the Mediterranean outflow water definitely has a higher pH signal associated with it, which would be consistent with the lower oxygen and the nitrate signal. And one more question for Ken. Can you expand your analysis globally? So that'd be, for example, Atlantic versus Pacific.
Yeah, that's for Christina. I'm actually thinking about the iron. I mean, iron limitation is
iron
everywhere.
limitation. Yeah.
Yeah.
I would like to accept there is not a single float with a radiometer around Ocean Station, Papa area, where it would be great to test this. So let's get some floats in there. The North Atlantic is interesting because at least in Colin Rösler's study, that also shows up as a somewhat high fluorescence to chlorophyll ratio with the HPLC comparison she's done. And we know that it's at least seasonally iron limited now. So I would actually wager this could be another indication that up there we see that as well. I think to keep my life easy right now, I will stick to the Southern Ocean. Especially there is also really reason to believe, I think, that Southern Ocean phytoplankton have very specifically adapted to that low iron they're seeing, like some of Robert Strapek's papers have shown that. And they might really therefore show a very specific way to fluoresce and have done things with their chlorophyll apparatus and stuff that might be really quite unique to the Southern Ocean. So I think for now I'll stick to that with this paper. But I mean, there's room to expand this, of course. And yeah, but I think this will be for now a uniquely Southern Ocean solution if we come up with a better way to calibrate the fluorescence there. But also that's where it's most urgently needed. Like for the rest of the ocean, the factor 2 isn't actually such a bad assumption for most parts.
All right. I'll throw out a quick question of my own and then add one from Eric. So you showed the KD chlorophyll from 490. So I was curious if there are more irradiance sensors with 440, if you think that would give you better sensitivity. And then the other kind of related question from Eric is just what instrument improvements or additions might help with both particle or spike detection and also the iron limitation studies. So go wild on what you'd like to see added. I saw a transmissometer on Nathan's picture, so maybe there's something there.
Regarding the KD490 question, I think actually Josh might be better to answer this, but from papers I've seen, there's usually when you have KD490 or like you have the 490 radiometer, usually have at least 2 others in addition to PAR. Usually it's a 4 wavelength situation, and they're usually lower wavelengths, but it does appear that they end up being more affected by things like CDOM and stuff. So I think they're not as faithful to chlorophyll as the 490. So I think for chlorophyll, particularly 490 is probably a better bet. But there might be things you can, ultimately try to look at, like species composition signatures or something, even in your KD. We know they have different absorption spectra, so that might actually be reflected in the attenuation. But I haven't seen anybody actually really try that, and it's a pretty long shot, I would say. In terms of other sensors, like I think what I'm quite excited about is the possibility to get fluorescence sensors that stimulate chlorophyll at different wavelengths. Not so much because I think they will tell me more about iron limitation, but that will tell us more about species composition. And that's definitely another huge factor that influences fluorescence properties and many other things. And so therefore also the calibration factor and stuff. Plus we know it's so important for, carbon pump, all sorts of things. So getting a better handle on that would be really, really interesting. And I think that there's work on that. I know that there's actually probably even studies being done on it already, or there might already be floats out there, but just prototypes. But I think that would be the sort of sensor I would want to get my hands on next. I don't think FRFs or fires or these, active kind of fluorometers for floats are really, I don't think that's going to fly very well. It's for gliders, that's great, but I don't see that on floats anytime soon. Anybody else wants to chime in on that?
Can I ask a question, Ru? This is Steve Reiser.
Yeah, please.
Yeah, Christina, in order to do the analysis you're doing, do you need the floats to come to the surface at a given time of day, or does it matter?
Well, it's actually something I thought about last night when I couldn't sleep. It's that's one of the annoying things is if you want to get a KD chlorophyll, you need basically midday rising of the float, so midday timestamp for the float. But ideally, your fluorescence would be much better served by having a midnight, surfacing. But you can't really always assume that within 12 hours you're still in the same water mass. So there are a few data sets out there. I think actually particularly right now some NKE floats that we have here in Australia that do day-night cycling, but not every day, just every 5 days or something. Where this could be tested if this works. So that would be sort of an ideal scenario, because the NPQ correction we know is also not perfect. So any kind of biases in that, of course, affect greatly what we do with this fluorescence per chlorophyll right now. And that again, also if we had a way to get, well, actually, no, that won't work. So yeah, basically the answer is yes, we do need daytime profiles to get KD 490 and therefore our chlorophyll right now. But the fluorescence would be better served by nighttime profiles. I think they should come close together in time.
One of the reasons I ask is there's an ongoing discussion in Argo about this right now, but the nighttime or day or noon profiles kind of start to defeat the idea that each of these floats is also a core Argo float, because the core Argo mission is to estimate the heat content of the world ocean. And if you're always coming up at noon or midnight, you get kind of a biased estimate of that. So there's more discussion that needs to go on about how to do this.
I think my answer to that is at the moment, there's still so few radiometers on floats out there that at the moment I would want to capitalize on them as much as we can by having noontime data. But the more it becomes the norm that we have radiometers, I'm all for randomizing it, because then we just have enough data. We don't need every single one of these profiles, So that's kind of where I'm standing there.
Christina, just sorry to interrupt, but we're running into our break time, so I want to give everyone a chance to step away for a little bit. I'm sure if anyone wants to continue the conversation, feel free to stay on the channel, but we will reconvene. We'll try to get back on schedule. So we'll reconvene at 2:45 to start up the breakout rooms. And I think, George, at that time, you'll give some little reminder of how to connect to those rooms.
That's correct.
All right. Thanks, everyone. Feel free to stay on if you like. There's another question for Faye about impact of typhoons and if there's enough Argo data to kind of separate the natural background variability from what you see in those events.
I'm typing the answers.
Tina, if you're still on, can I ask whether you've looked at KD 490 closer to dawn and dusk? Because from what I've seen, it looks like you're getting information, some KD information near the surface, less you don't have as much squinching. And you have to be careful about the changing sun angle over the course of the profile. But if you correct for that, I think you may be able to get useful KD at lower sun angles and then also get the unquenched chlorophyll. And then maybe
Yeah, that would be worth testing. And I mean, I can't actually say on top of my head. I'm sure there is actually probably an influence on, I mean, it's a diffuse attenuation coefficient and it is affected by sun angle for sure. So you would get, but there's probably some sort of correction you could do for that, but you then have to assume some sea state or whatever, a little bit more maybe. I don't know. It would get complicated. Unfortunately, it's not really possible with the float data at the moment because I have to double check this. It's on my to-do list, but I'm quite sure that the NKE floats all actually surface around noon. Like that's what the French do right now. At least the ones in the Southern Ocean. So
there is some low sun angle data from floats that have done sort of deal cycle type of sampling.
Okay.
But yeah, I'm sort of optimistic that more of the deal cycle, if we have floats sampling randomly throughout the day, that actually a good fraction of that will be useful. If
I do agree. Yeah.
Deep KD down into the deep chlorophyll maximum, for example, it's really only around noon that's going to be useful.
Yeah, and yeah, I'm also a bit, I don't know, I'm not really sure. Well, yeah, it's nice if we get there, I suppose, but I would say that it's on my lower priority list. Like getting 1 KD per profile, I'd be quite happy with overall. And also, isn't there that paper by Zing, that the more recent one, where he actually does some fancy stuff to get KD along the profiles? He just doesn't see a big difference even for the chlorophyll maximum. So it seems to me that it may not even really be that necessary to, to get different calibration factors for fluorescence for different parts of the profile. It doesn't quite seem to be as big of an issue, at least in what he showed, as we might have thought.
Okay.
Nathan and Christina, this is Josh. What do you mean about the at depth? You're not seeing a difference in the relationship between fluorescence and chlorophyll?
Well, I haven't looked at it, but if you look at it's one of the more recent Zing papers, the one where he really goes to town on getting using the fluorescence sensors together with the radiometer to get a better fluorescence calibration, but really going along profiles, like doing different fits along the profiles and so really trying to get a depth resolved answer there. And I think his conclusion is that there isn't really much to resolve. Like it's
a depth resolved KD.
Yeah. And therefore then a depth resolved correction for the fluorescence.
Got it.
And it doesn't seem to really be that important to do that extra step, I guess.
But the fluorescence to chlorophyll response probably does change throughout the profile. Like in the deep fluorescent maximum, the ratio is probably not the same as at the surface. Is that correct?
Well, I feel because he has done the resolved KD, he got that too, and he felt it didn't matter so much. I have to double check.
Okay.
But that was sort of what I took away from reading it.
I think that the big effect, the packaging effect, will affect both fluorescence and KD, right? Because it's based on absorption.
Right.
First, right. So you're going to reduce your absorption per unit of chlorophyll in the deep chlorophyll maximum, but that may not show up as a change in the KD versus fluorescence slope. But
but then I would say if that is true, then and you get a better calibration for your fluorescence even from your surface KD, then you can basically get your KD in the deep chlorophyll maximum from that better chlorophyll estimate. But then you just do it reverse. You use your fluorescence to get your chlorophyll and get your KD. Wouldn't that work? Like, do you really need to resolve your KD all the way into deep chlorophyll maximum then? You just need one.
Right.
Yeah, I mean, I think I would have to convince myself that that's a robust result. Because certainly, if you look at KD, depth resolve KD, the KD itself gets much higher when you get into your deep chlorophyll maximum. I haven't specifically looked at the KD to fluorescence ratio, but you know, I would want to see a lot of data before I concluded that that in general throughout the global ocean, there's no information there.
But so that is implying that all of these deep fluorescent maximums are chlorophyll maximums. Am I understanding that right? Is that what you're saying?
This is Ian. I would not go that far because it's a particle maximum. Doesn't necessarily mean it's your chlorophyll maximum. They're usually certainly within the equatorial Pacific, you're going to get an offset within, maybe only 10 meters, but between the particle maximum and either the packaged or the express chlorophyll maximum.
Yeah, that's what I thought. There was a Jackie Long and part of our lab group had done some neat work, I thought, on Station P showing that, the chlorophyll concentration remains quite constant, but the scaling factor, if you measure the fluorescence, it's quite variable, and it can peak at the deep fluorescent maximum, if I'm remembering correctly, yet the chlorophyll concentration is not changing.
Right. I mean, that's the whole NPQ backscatter analysis is based on your particle concentration is relatively stable. It's just your chlorophyll response. If I can comment one on the KD, I mean, it's really that transference between the inherent and the apparent optical properties. And because I come from the IOP field, I tend to think of the AOP as an integrative from the surface data point. The more I haven't read the Zing paper. I will go find it.
It's 2011. I'm actually just looking at it. I'm looking for the quote.
Okay, well, I should be familiar with it. But the more you integrate it to the same particle mass or the same volume rather than integrative, the closer they should get. But then it just becomes how good is our sampling tools?
And the one thing sorry, Christina.
Can you just repeat what you just said, Josh, for line P? So they found the fluorescence per chlorophyll of chlorophylls measured by HPLC is higher in the DCM.
No, that like the chlorophyll itself, and I hope I'm not misspeaking, but I think I remember looking at a plot where the chlorophyll is relatively constant through the water column, but at the deep fluorescent maximum, the fluorescence goes way up, but the chlorophyll does not.
Yeah. Can you hear me? I'm not sure if my microphone works on this computer.
Yeah.
This is Jackie.
Yeah, we hear you.
Oh, great.
Yeah.
Yeah, so we compared HPLC data from line P with nearby float fluorescence and also the co-located fluorescence on the CTD sensor. And you actually see a heightened fluorescence to chlorophyll with depth that's like subsurface. So the issue with that was and this was after applying the Shin correction for MPQ. If you wanted to say correct the float fluorescence using satellite data, your offset would be biased because if you're applying the same ratio through depth, that's an issue because it's actually variable.
Do you have any nighttime fluorescence data though? Because like especially if you're on a on a CTD and stuff, because I mean, as much as the Zing correction seems to work with floats and in the Southern Ocean actually particularly well, it seems to work. I'm not sure for other regions, but I'm just always hesitant to draw big conclusions when the only fluorescence you have is actually a NPQ corrected one.
So it was both daytime and nighttime. This is over 10 years of line P data.
Okay. And then that's constant. It always goes up with depth, the fluorescence per chlorophyll.
No, I would have to look. I mean, it might be even a seasonal relationship.
Yeah. Because it's, I don't know. It's hard.
I just thought Jackie's results were super neat.
Yeah. I mean, it could be species composition.
Yeah,
I mean, that's
yeah,
the
it
thing.
could be
There's
changing
no,
with depth. And then I did a similar analysis with the data at HOT, and you kind of see the opposite effect where there's a steeper increase in HPLC see total chlorophyll A, but it's not associated with a linearly similar increase in fluorescence. So your ratio at the surface isn't the same subsurface, basically.
This is Eric. I just wanted to throw out something kind of wild. What if we had multispectral LiDAR-based KD or KSIS? You know, so you don't need the sun. So it's still kind of an apparent optical property, but you control the sun because it's your laser. And you get multispectral, and you still have your fluorometer. So it all works at night.
Eric, I'm going to encourage you to take that idea to the float technology breakout room. We're at our time point to start the breakout rooms, and so you'll see the options pop up there. So our goal in each of those breakout rooms will be to have a discussion for 45 minutes, and then we'll have 4 minutes available for a report out.